for joining us. My name's Luc. I'm a sales engineer for PCI. I come from France, so please excuse my accent. I'm joined here with Amélie, which is our marketing manager at PCI Membranes. Today, the goal of the webinar is to discuss wastewater and membranes. So, just a few groundkeeping rules. I'm going to make the full presentation to you in English. Should you have any questions, you can put it in the Q&A section, or we will have a Q&A session at the end of the presentation. In any case, you'll have my contact information at the end of the presentation, and I will be more than happy to answer to any question you might have. And I will be able to send you the presentation and send you more information about what is going to be discussed today. So, Amélie, do you need to add something, or shall we start the webinar?
Everything is great. Thank you very much, Luc. Please go ahead.
All right. So I'm going to share my screen with everyone. Okay, you should be able to see my screen now. Is this correct, Amélie?
Yep, perfect.
Okay. So let's start. Today we are going to discuss wastewater treatment and reuse with membranes. Again, I'm Luc from PCI Membranes. I'm French. I've been in the water business for 15 years, with PCI Membranes for 1 year now. The table of content will just briefly introduce PCI Membranes for those of you who don't know our company, just so you know who we are and what we do. And then we'll move on to the effluents, the wastewaters, the sources and characterization, as it's really important for treatment with membranes. And then we'll go to the heart of the presentation, which are needs and solutions. What are the needs in terms of wastewater treatment and the different solutions we can use with membranes? We'll then have some case studies, because theory is nice, but it's always more interesting to see real-life solutions. There will be a very small conclusion and a Q&A session. So please feel free to note your questions, put it in the Q&A section, or we'll do it at the end, or I will be available after the webinar if needed. So PCI membranes. PCI membranes originates in the 60s in the United Kingdom. It was first developed for seawater desalination with tubular membrane, and then it moved to other applications. The business really started up in the 80s. What's important to know is that in 20 years ago, we moved to Poland. So we are now a Polish company, so part of European Union, and our manufacturing plant and legal entity are close to Poznan in Poland. 7 years ago, we were acquired by Madison Industries, which has a filtration group. Filtration group, we are a group of 29 companies, all dealing with filtration. Could be filtration of air, of effluents, of liquids. We all have different specialties. Our specialty at PCI Membranes is the filtration of liquids using organic membranes. Our presence, so our head office, manufacturing plant, customer service, R&D is all located close to Poznan in Poland, so Central Europe. We still have a small technical office in the United Kingdom, and then we have sales staff and technical staff all around Europe. For example, I am based in Tours, which is between Paris and Bordeaux in France. We also have a global network of local partners all around the world. And our sales staff is not only in Europe. I have colleagues in USA for the Americas and colleagues in China for Asia as well. So please do not hesitate to contact us to get your local contact for PCI membranes. What do? We do microfiltration to reverse osmosis. So, as some of you might know, from MF to RO, we go to tighter and tighter. It means we can filtrate smaller and smaller components. Microfiltration will be used to reject suspended solids and bacteria. Viruses will go through. If you want to remove viruses, you'll have to move to ultrafiltration. Ultrafiltration will also remove some macromolecules, the big molecules. If you need to go to smaller molecules, then you need to go to nanofiltration. And nanofiltration will also remove multivalent ions, which are the salts dissolved in water with a multivalent charge. Finally, if you want to remove everything up to the singly charged ions, you'll have to move to reverse osmosis. PCI membranes can offer all this range, and we can do it in several types of geometry, which I will explain later can have different advantages. Our main membranes and main geometry is tubular. We do MF, UF, NF, and reverse osmosis in tubular form, which is quite unique, technologically speaking. This is quite a unique feature of PCI membrane. Our hollow fiber is only UF, which is used for submerged MBR. I will come back to this after. Plate and frame is reverse osmosis, which is used specifically for landfill leachates. And finally, spiral wound membranes, which are largely used in the market as polishing of wastewater. I will show to you every geometry and everything we do later on. Our services. We are a company that loves to develop new applications and do trial and testing. We have a fleet of about 10 pilot units that we can use in-house in Poland, or we can use on-site. So we run lots of trials. Either we receive effluents in Poland and we do the trial in Poland, or we send our pilot on site. And with this, we can do lots of trials, mainly with tubular and spiral wound membranes. It allows us to clearly define if the membrane is the right one, if it's possible to do it, and to carefully design a commercial plant. And then in terms of delivery, of course, we are a membrane manufacturer, so we supply membranes and modules. But if you need a wee bit more from us, we are also able to supply you frame, stacks, racks, or units on skid or containers. We'll use subcontractors, but it's something we can do for you. If, I don't know, if your agenda is too full and you need some help, we can do it. We also supply on-site services, and a really interesting feature is that we supply engineering packages. If you are building your first tubular filtration unit, we are able to help you supplying engineering packages for you to carefully and correctly build your unit. So please do not hesitate to contact us if you need this. Okay, let's dive into our subject today, which is basically wastewater. So the effluents we are talking about. Wastewater can come from lots of different places. I will just discuss the main ones today. Obviously, we all know about municipal wastewater. Every city has to have a plant to treat this municipal wastewater. We also have landfill leachates. All our waste is going to a landfill, and then with humidity, there's a collection of liquid that got all the bad stuff from the waste, and it's called a leachate. It's a quite difficult effluent to treat, but it can be treated with membranes. And then a major part of what we do with wastewater is industrial wastewater. So any type of industry can have wastewater, can be food and bev, can be mining, can be chemical, textile, electronics. And it's really important for them to treat their wastewater in order to release it either to the network, either to nature, or to be able to reuse the water. More and more, we want to reuse our water, and membranes are one of the best solutions to do it. Other types of wastewater can include condensates. which can be treated with membrane. And please do not forget that in every plant you have, you need to do washing, CIPs, cleaning in places. And those solutions, those spent solutions, can be recycled with membranes. So it can be a further saving on money and further savings on water. The most important thing to do before you treat your wastewater with membrane is to do a characterization of your wastewater. If you have a problem, you need to clearly define your problem and what you want to do before you choose the best geometry and the best membrane and the best solution. Sometimes the membrane is not the best solution, but to know about this, you need to characterize your wastewater. So it's really important. Get as much info as you can. Okay, sorry, I have a glitch in my screen. Okay, it's back. So here are the main parameters we will look at. The temperature of the wastewater. It's important to know your minimal and maximum temperature. First of all, because membranes cannot withstand every type of temperature. Some can go up to 80 degrees, some can go up to 30 degrees. So you need to know the limit in order not to harm the membrane. And then the temperature will change the viscosity of your effluent and the viscosity of the membrane. So the flux, ejection of the membrane, and the operating pressure will not be the same depending on the temperature. So it's really important for you to define this. Same for pH. Some membranes cannot withstand every type of pH. Some will be limited to 1.5 in acid, 10.5 in alkaline. You have to carefully check this not to harm the membrane. And then it will also change the composition of your effluent. For example, the solubility of salts and metal will not be the same at a pH of 4 than at a pH of 10. So it's really important for you to get this data. Suspended solids are the dry matter which is in suspension in the water. It will be removed by every type of membrane, of course, but you'll have to be really careful of the amount of suspended solid you have in your water. Depending on your geometry, you will have to pre-treat it or not. So because suspended solids can clog and foul the membranes. Organics, which are basically TOC, BOD, COD, it's organic material in the water. It's important to characterize because it can foul the membrane, and most of the time, especially in some wastewater treatment, it will need to be removed. So we need to know what is the amount in the water, in which form, if possible, so we know which cutoff to use and which goal you need to set in your permeate. So it won't be removed by MF, only big molecules by UF. So most of the time we use NF and reverse osmosis to remove the dissolved organics. In terms of biology, bacteria and viruses will be removed by UF, NF, RO. Bacteria can be removed by MF as well. So it will be removed by membranes. However, if you need pathogen-free water, it's usually recommended to add a safety step after membrane like UV or chlorine. An oxidant, disinfectant is just an extra step to be extra sure. Metals, they are in soluble or solid form. Solid form will be considered like a suspended solid, but you'll have to be careful. Metals can be abrasive. And membranes, they do not like abrasion, apart from one type of membrane. Soluble form, usually for membrane treatment, we oxidize, precipitate it to put it into solid form to be removed by membranes. However, the soluble form, it will be removed by reverse osmosis, but it can foul the membrane. So the lower the soluble content, the better it is for membrane treatment. So be careful of metals. Fat, oil, and grease. Membranes do not like fat, oil, and grease. So it will lead to fouling, and it's usually a fouling that's quite difficult to remove and to clean. Some geometries can allow you to treat small amounts, especially tubular membranes. So usually below 100 ppm, but normally in almost every time we remove this before membranes. Solvents have to be characterized because they can harm the polymers, the organic membrane. So you need to characterize it. Chlorine will be okay for MFUF because the polymer used in those applications are resistant. But if you are using NF and RO, it's usually polyamide. Polyamide does not like chlorine. Chlorine will oxidize the membrane and it will be destroyed and cannot be fixed. You'll have to replace the membrane. So please be very careful of free chlorine with polyamide in NF and RO. Finally, salinity. It's very important for NF-RO application. As we have seen before, NF and RO will remove the dissolved salts. And as you know, there's an osmotic pressure phenomena, and we need to know the salinity because it will directly impact your filtration unit. Beware also of scaling. If you concentrate salts too much, it will start to crystallize and it will foul your membranes. You can use acid and antiscalants to prevent this, but it has to be characterized for any NF-RO application. The most common pretreatment we can find before membranes are those ones: screenings to remove the coarse solids. We can see some biological treatment and settlers, for organics and suspended solids. Dissolved air flotation, it's usually the same organic suspended solids, but it's mostly used for fat, oil, and grease. Coagulation, flocculation, settling, suspended solids and metals. And then if you want to treat metals, you can also find some aeration, oxidation, chelation to transform the metals from dissolved to solid form in order to treat it more easily. That's it for the water. I want to emphasize again, it's extremely important to clearly define your wastewater before you move on to the solution, because the characterization of your wastewater will lead you to the correct solution. Needs and solutions. That's what we are going to discuss today. So I will go through every solution and need, but basically here's a summary. You might want to treat a difficult wastewater or a leachate. You can do it directly with tubular membranes. Advantages is that tubular membranes do not require pretreatment or a very minor one. It's very resistant to clogging, fouling, this geometry. PCI has the full range, MF, UF, NF, RO, which is quite unique. Second case, you might want to treat a wastewater with abrasive material. We have seen that some membranes, they do not like abrasion, but there is now a new type of membrane which is resistant to abrasion. So you can do it as well. Same if you have an extreme pH. Now we have tubular membranes resistant to 0 to 14 in pH. So you can use membranes as well on extremely powerful pH effluents. If you have a biological effluent and you want to clarify it, you use what we call a membrane bioreactor. You have two types of membrane bioreactor. You have the side stream MBR, which is an external one using tubular membranes, or a submerged one. We will come back to the advantage of each technology later on, but you can see here a summary, and I will come back to this subject after. You can treat leachates with maximum recovery using plate and frame and maximum pressure. Finally, spiral wound membranes can be used for easier wastewater, which is water that's really well pretreated because we need an SDI below 5, which means almost no suspended solids in the water. And usually spiral wound membranes are used as a polishing step after a first step of membrane, which can be hollow fiber or tubular. Then we need to polish the effluent and we'll use spiral wound membranes. I will now show you every type of need and solution. So let's say you have a difficult wastewater or a leachate. It's a difficult effluent and you want to do a one-step treatment, directly treat it. Then you'll have to go to tubular membranes. Tubular membranes, it's a geometry that's suitable for high viscosity, high suspended solid, high organics, because it's highly resistant to fouling and clogging. We are using tubes of 6, 8, and 12.5 millimeters in diameter. So it's very difficult to clog it. It's robust, reliable, it's easily maintained. Usually you don't need pretreatment, so it's a one-step treatment. We don't need lots of chemicals to treat it. It's also possible to do a mechanical cleaning on this geometry using foam balls. So mechanical cleaning allows you to do more advanced cleaning and to use less chemicals, which is specific to the tubular geometry. It's very modular. It's a very easy to use membrane, and we can do MF, UF, NF, RO. It has two disadvantages, though. One, the membrane area in tubular form is quite low due to the geometry, and two, you need a recirculation pump to get a good cross flow into the tubular membrane, so you'll use some energy. But apart from that, it's very efficient. There are lots of different types of membranes, 6 different polymers, and cutoffs ranging from 0.2 micrometers to reverse osmosis 99% rejection of sodium chloride. So as you can see, you can select the right polymer, the right cutoff, and the right module for your treatment. It's a really nice versatility of different solutions you can choose from for your specific effluent. And as you can see, some membranes can withstand up to 80%, 80 degrees Celsius in temperature, which is really interesting. Modules, we have different types of modules with different sizes. I don't want to go too much into details today. Obviously, if you have a specific subject, we can discuss it in more details later on. But basically, those modules are used with tubular membranes from MF to reverse osmosis. I just want to show you a typical PNID, just to show you, pointer. Just to show you a typical PNID. Usually for a tubular unit, you'll have a feed pump that will feed your effluent into a recirculation loop, where basically you have your tubular modules in series and you recirculate it to keep a really high cross flow. And from this loop, you get permeate and concentrate. And of course, you have your flushing cleaning unit for which you will be able to flush and clean the membrane. Here are the recirculation needs depending on the type of modules. As you can see, those are quite high flows. So it's important to know that for tubular treatment, you need quite a high flow recirculation loop. But that's what makes it so efficient and resistant to fouling. As I told you, polymers used in organic membranes, they do not like abrasion. They do not like extreme pH, so which is a limitation of this technology, unless you can come up with a new technology that PCI came with called TMF. TMF is a different type of tubular membranes, which is resistant to abrasion and resistant to extreme pH. Why did we change? We changed the mechanical support. Instead of tape, we are using a polyethylene substrate, which is basically produced by a sister company of the filtration group. Inside the polyethylene, we inject PVDF. So it's not just a layer of PVDF, it's PVDF inside polyethylene. Makes it extremely resistant. You can backwash it, you can backpulse it, you can treat 0 to 14 in pH, you can treat abrasion, abrasive materials. So it opens up a new era of applications with organic membranes. Recovery of metals, recovery of minerals, abrasive suspended solids, recovery of acid, caustic, extremely concentrated chemicals. That's extremely interesting. That membranes being PVDF, it comes in NF and UF. So 0.1 to 0.02 micron. That's a general skid that's used for this TMF technology. You'll have a concentration tank a recirculation loop into the TMF modules, from which you will get filtrate and concentrate. You have a backpulse column or a backwash pump. Backwash pump, you all know about this. Backpulse column, it's a column of filtrate water, which you can push with compressed air instead of using a pump. And of course, you'll have a frame and CIP and flushing tanks. It's quite standard. Now, let's move to membrane bioreactors. What do you do when you have a biological treatment of your wastewater? The most common treatment is to have a biological tank with bacteria treating the organics. And then you have a settler to separate the biomass from the water. Settler is nice, but it takes time and space. If you want, you can replace the settler by membranes. That's a membrane bioreactor. Two types of membrane bioreactor. First one is side stream, which is an external filtration unit using tubular membranes. The second one is submerged MBR, which is a very common one, where we put membranes inside a tank with the effluent, and we will suck the water out of the tank, leaving the biomass and the suspended solids inside the tank. Those are the two solutions that are used in membrane bioreactor. What are the differences? On your left, you'll have tubular side stream. On the right, you have hollow fiber submerged. So first of all, tubular, you'll have better choice of cutoff. You have 4 different cutoffs, while in submerged, you only have 1. Packing density is unfortunately low in tubular membranes. As we have seen, the membrane area in tubular geometry is very low. It's quite high with hollow fibers. So that's an advantage. You need less space. The MLSS content in the biological treatment has to be in quite a narrow range for submerged. It's 8 to 10 grams per liter, can go up to 12, 14 in some cases. The advantage of tubular is that it's flexible. Can be very low, can be normal, can be very high. It's quite versatile, and it's really an advantage. Fouling sensitivity, tubular membranes are extremely resistant to fouling, while hollow fiber are more sensible to fouling. So you need to be more careful with hollow fiber. Electrical consumption, very high with tubular because of the recirculation pump, quite low on submerged. And then air consumption, you don't need air with tubular membrane, you need aeration with submerged MBR. Chemical, it's very low with tubular because it's very easy to clean, and you can also clean it mechanically. Ease of installation and ease of maintenance, it's much easier with an external unit using tubular membrane than with submerged membranes inside a tank. You don't need civil work with tubular, and you don't need to take membranes out of a tank. So these are the main differences. As we see, mostly submerged hollow fiber are used on big projects, usually municipal projects, because of the high packing density. And tubular external MBR are more used on smaller projects and smaller industrial projects because it's much more versatile in terms of MLSS content. So that's what it looks like. On your left, you have a module with tubular membranes, and on your right, cassettes with hollow fibers. So these are some characteristics. So tubular membranes, we've seen it, and 2 types of cassettes, standard continuous aeration or pulsed air aeration. This one use a height that's higher because of the box, but it will consume less air. So there's an economy in energy for this one. Plate and frame. Plate and frame, it's used when you want to go to the highest pressure possible, so up to 140 bars. It's specifically used on leachates to go to the highest recovery, basically. I won't discuss it too much, but basically, usually you have leachate, pH adjustment, multimedia filtration, and then you have 1 or 2 steps of plate and frame. And if you want, you have the option to do a polishing with spiral wound arrow. So basically, highest recovery, highest pressure for landfill leachates will use this geometry, plate and frame. Finally, the last geometry is spiral wound, which is quite well known on the market because of its really high packing density. It requires to have a clean water. Okay, your wastewater needs to be really well pretreated for an SDI below 5, or it has to be pretreated by a first membrane step. But then you'll have a very high membrane area per module, a low footprint. Basically, it's cheap. And we can offer you NF and RO in this. We have some NF with chlorine tolerance, which is quite nice, and I will show it to you. And then our standard elements use 46 mil spacer, which is thicker than most suppliers because we specifically target wastewater, and the thicker the spacer, the lower the fouling. So it will be easier in terms of operation and maintenance. So 2 ranges. The first one is called the Dura, which has a standard spacer, 28 mil, and the standard membrane area, standard compared to the market, but it has chlorine tolerance, up to 10 ppm continuously and up to 100 ppm in cleaning, which is really interesting. And then other type of membranes, which are not chlorine resistant, will have lower membrane area, but a 46 mil spacer, which is clearly targeting wastewater for lower fouling and easier operation and easier cleaning. So we have seen several needs and solutions in terms of wastewater and membrane treatment. That's theory. Let's move to real life. Today, I wanted to focus on tubular membranes for the case studies because this is what we mostly make at PCI Membrane, and tubular membranes are not well known on the market, and it has really nice applications. So I wanted to discuss something that is not really well known on the market. So mostly tubular membranes today. First case study will be potato wastewater. The end user is a potato processing plant in Europe. They needed to concentrate and recover protein and potassium from a wastewater that was quite hot, up to 70 degrees. We've made a trial and we've defined a solution, which is a tubular RO unit, as you can see on the right, with AFC 99 membranes, 99% rejection. It's polyamide, tubular form, 12.5 millimeter diameter. 720 modules, concentration factor 3, up to 70 degrees. And for cleaning, we use foam balls and chemicals. Foam balls allows to decrease the chemical usage and increase the efficiency of cleaning. Advantages for the end user: much cheaper than evaporation, excellent permeate and constant permeate quality, and it's a one-step treatment. It's tubular, no pretreatment, it's reverse osmosis. So they don't need to do UF plus RO. They only have one unit, filtration unit, for their problem. Next case study, paper wastewater. Still in Europe, paper pulp producer. From their bleaching stage, they have some wastewater which has COD in it, 10 grams per liter, with lots of wastewater. They wanted to concentrate 50% of the COD in 2% of the incoming wastewater, so a recovery of 98%. Solution: we used a UF unit with tubular membranes, specially developed for this project. And then we used B1 modules. So combining B1 modules, which are stainless steel modules with a UF membrane, we were able to go from 300 cubic meters per hour of wastewater to only 6 cubic meters per hour in final concentrate. So only 2% of the incoming wastewater is a final waste. So if you only have 2% going to incineration, of course, you'll make lots of economy. You win lots of money. And the end user, he was able to obtain the SWAN ecolabel for its plant. Washwater effluent. As I say, membranes can also be used to recycle washwater or CIP water. And it's really interesting application. The end user is a producer of hygiene and personal care products. They had washwater containing laundry detergent. As you can see, some of its characteristics. The problem is that the concentration and the viscosity of the washwater was quite versatile. So it's not always the same concentration, it's not always the same viscosity. After trial, we defined that B1 modules with AFC 99 RO tubes, 12.5 millimeter tubular with foam ball and chemical cleaning were quite efficient. Why? Because it's a one-step treatment. It's adaptable to various types of quality and viscosity, which was the main issue of the end user. The tubular membranes can adapt to different types of concentration and ever-changing wastewater. And they reuse the permeate. So they are saving some water and some money. So they are quite happy about it. Next case study will be a leachate after a biological treatment. In a European landfill, there was an existing biological treatment, and they wanted to recover the biomass from the biological treatment and concentrate the waste. So it's a two-step treatment. One, we used tubular UF in order to concentrate the biomass. Factor of concentration is 10, and it's returned to denitrification. The filtrate goes to a tubular RO using B1 and AFC 99, so we can concentrate the UF permeate. Concentration factor 5, concentrate being the final waste. So we reduced a lot the flow of wastewater. RO permeate from tubular is polished through a spiral 1 unit for reuse. So because there are still a few salts and a few molecules in it, so it's just a last step of polishing before reuse. That's really nice. So as you can see, we have low fouling on tubular membranes. The polishing unit with spiral 1 has a high packing density. If you take the 3 units, the global concentration factor is over 5. So they saved a lot in terms of evaporation costs. Leachates can also be treated directly with tubular RO. Same in the European landfill, no biological treatment. There's variation in volume, variation in quality, and we need to concentrate it as much as possible to reuse the final waste and also to reuse the water. They used 1 unit of tubular RO membranes, concentration factor 12, and of course what they loved. It's a one-step treatment. It has low fouling thanks to tubular technology. They can have lots of variation in terms of volume and quality of leachate, and they recover 92% of the wastewater that they use internally as reuse water. So savings on evaporation, savings on water, savings on space because it's only 1 unit. So it's really nice. Conclusion. As we have seen today in our webinar, you'll have lots of options with membranes, okay? It's not one problem, one solution. But what membrane will provide you, it's an excellent quality of treated water and possibility to reuse this water for lots of savings. As I have said, one problem can have different solutions. It's very important to define your problem and what you want to achieve to define the different solutions. And as you can see, there are 6 different polymers, 4 different geometries, So the possibilities are almost endless. Please define correctly the wastewater to be treated, the pollutants to be removed, the targets in terms of permeate concentrate clarity, and the concentration factor you would like to achieve. If the application is known, it can be directly designed into a commercial unit, but in lots of cases, because we love at PCI the difficult cases, we'll go through trials, because we love to develop new application and to treat wastewaters that have never been treated before, or to improve existing processes. Again, as I said, one problem, different solutions, and that's what's really interesting with membranes. It's time for Q&A. It's been 40 minutes, so we have 20 minutes left for Q&A if needed. So please shoot easy ones, please.
Thank you very much, Luke, for your presentation. So first of all, we've got a question from Mark. Mark would like to ask you the use of a recirculating pump in our proposed design. Is it absolutely necessary if the required cross-flow velocity is already achieved by the feed pump?
No, if the velocity is already achieved by the feed pump, no, you don't need a recirculation pump. But in 90% of cases, the feed pump, it's only a small flow and it won't be able to achieve the required cross-flow velocity. But exactly right, if the feed pump already has the required flow and the cross-flow velocity is achieved, you don't need a recirculation pump.
Okay, sounds great. Thank you very much for answering your question. I hope it has answered the question Mark has already have. Nevertheless, Mark, if you'd like to discuss more in details, we can still schedule another call with you. You're welcome, Mark. Then I got another questions regarding the application of membranes. So are the membranes only used on wastewater?
So today, the subject of our webinar was wastewater, but no, membranes are not only used on wastewater. They can be used to produce processed water for industry. They can be used to produce potable water. Our example at PCI Membranes, we have the DWI approval. So we produce drinking water in the UK. Because we have this approval. And also, a big part of PCI membranes application in business is process separation. So the membranes are also used to treat food and beverage effluents. Could be milk, could be wine, could be beer, sauce, juices. And we also work a lot with pharmaceutical companies to do pharma, biotech, effluent filtrations.
Yep, that's very clear. Yeah, we do cover a lot of applications, and water, wastewater is one of it. If you have other application where our membranes are able to help, please contact us. We can discuss more about it.
It's important to note that sometimes in a plant we'll be present in two places. One in production plant where we'll process the product. For example, let's say a milk factory. We'll process the milk using our membranes, but we'll also be present at the wastewater treatment plant to treat the wastewater from the milk production. So we can do both.
Yeah. Meantime, I've launched a poll during our webinar session to ask our participants if they would like to be contacted by our team to discuss more about our wastewater treatment solutions. So let's take 3 minutes, wait for our participants to fill it out. I see Mark has another question regarding the case studies. We can also answer the question while we are waiting. So look, in the case studies you have shown where there are sometimes hundreds of membranes in use, how can you identify any that have failed, for example, by abrasion?
Okay. Those have not failed by abrasion because there's no abrasive material in the effluent. But basically, abrasion, you will see that you have a passage. If the abrasion is only on the membrane layer, you'll see a passage. Let's say you are treating COD. You'll find that COD is spiking up in your filtrate. Or if you are treating a salt, the salt will be spiking up in your permeate. That's where you can find some abrasion. The biggest case of abrasion, there will be a hole in the membrane, and if you put some air, you will find some bubbles. But basically, when there's abrasion, you will see it very clearly because the quality of your filtrate and permeate will degrade very quickly.
Okay, thanks, Luke. Let's take another half minute waiting for our participants to fill out the poll. And meantime, if you have any additional questions, please feel free to drop it in the chat or in the QR function. I do have another additional questions. Can you please answer?
I think we have lost Amélie. Amélie, if you can hear us, we've lost you. Okay, you're back, Amélie.
Yeah, my apology. I had a connection issue. I'm back. I see we are at the last slide.
Okay, you said there was another question?
Yeah, I do have another question. What is the typical lead time for our products?
Okay, lead time. Lead time. Well, when it's on stock, it's just transportation time from Poland. Okay, our plant and stock is in Poland. Then, if we need to produce the membranes, well, it depends. Tubular membranes can range from 1 to 3 months usually. Hollow fiber membranes can range from 3 to 5 months. Spiral wound membranes can range from 2 to 5 months. Obviously, it depends on our production calendar. So those are typical lead times. So please do not hesitate to contact us. We'll tell you if it's on stock or not. If it's not on stock, we'll give you a typical lead time. So on stock, quite easy. And then if you need to produce it, anywhere between 1 to 5 months, depending on the geometry and reference.
Okay, perfect. Thanks, Luke.
Okay. Well, if there are no more questions, please find my contact here. You'll have my email address. If you have any more questions or you wish to discuss or have a specific project, please contact me. You can also contact me to have a copy of the presentation. I have it in French also, if there are some French speakers here. Finally, if you want to meet us in person, Amélie and I will be in Rennes, France, at Carrefour de l'Eau in January next year. And if you want to meet the full team of PCI Membranes, the full team will be at Aquatech Amsterdam in March next year in Netherlands, in Amsterdam. So please do not hesitate. You have our booth number, and we'll be more than happy to welcome you and discuss with you. And that's about it on my side.
Great. Thank you very much, Luke, for the excellent presentation. And thank you, everyone, for joining us for this session. If you have any questions, please feel free to reach out to us. Then we can share more details with you. Thank you.
Thank you again, everyone. Thank you, Amélie. Merci à tous. Au revoir.
Thank
Goodbye.
you. Have a great day. Bye.